This is Mrs. Gunlock again, and we are starting chapter 6 and 16 in the zumdahl textbook, which is actually chapter 5 and 19 in the Brown textbook on thermodynamics. So let's get started. Thermodynamics is the study of energy and how it flows between the system and its surroundings. And one of the big reasons that we care about thermodynamics is the concept of whether a reaction will occur spontaneously. And by spontaneously, I don't mean without any reason for happening or all of a sudden, but it means if you mix the things together, does it go or does it just sit there? And this is really important for chemists because chemists are people that mix things together. And if you're standing there when it is reacting and that reaction is explosive, then you hurt yourself. And so you just kind of want to know, does it go? Does it not go? How much is it going to go? Is it going to go with a lot of energy? Is it going to suck a lot of energy in? Thermodynamics answers these questions. There you go. That's thermodynamics. That concept that I talked about, spontaneous versus non-spontaneous. Apparently the AP people prefer thermodynamically favored. I'll try and remember to say that, but I'm really probably going to say spontaneous because it's a lot easier. So if a reaction is thermodynamically favored, that means that it will go as it is written. So if you have the reaction written out as H2 plus O2 yields H2O, does that go? It does. So that means that it is thermodynamically favored. It is a spontaneous reaction. That doesn't include the concept of activation energy. They're assuming that you would have the activation energy to go. However, if you flip that reaction backwards, H2O yields H2 plus O2, does that go? No, it doesn't. We have not really observed in life that water frequently, spontaneously decomposes into hydrogen and oxygen. In fact, you have to put in a constant supply of energy to supply the energy that it needs to continue. So the decomposition of water is non-spontaneous, whereas the making of water is spontaneous. So we've got spontaneous, which is thermodynamically favored, which means that the thermodynamics of this situation is that it will go, whereas with non-spontaneous, it's not thermodynamically favored, which means that the reactions are not going to go forward as written unless you put in a whole bunch of energy to feed it and make it go. If you flip them, they would go that way. So the big thing that we want to know is whether that process is spontaneous or non-spontaneous. And one of the things that you need to know about in order to understand this is your first law of thermodynamics, which is that the energy of the universe being constant, okay, energy can be converted or flow, but you cannot create or destroy energy. So that means that what you can do is follow the energy through going, I had energy here, where did it go? Because I know it didn't disappear because the energy of the universe is constant. So did it become potential energy in my system? Did it exit the system and go into the surroundings? And one of the things that you need to consider is the word universe here. Paste options. The word universe here, which is the energy of the universe is constant. So of everything around, we've got a certain amount of energy. When you start breaking it into, I'm only considering this system, this, for example, the Earth. The Earth is not the universe. So, there's energy coming into the Earth from the sun. And so, if you weren't aware of the energy of the universe being constant, you would say, oh, well, no, the energy isn't constant. We have a constant supply of energy coming in. Well, you've broken that into the system and the surroundings, where you've set the Earth equal to the system and the surroundings being, space and the sun. So be aware of that distinction. Because of the first law of thermodynamics, it's easy to to consider changes in energy, where it's like I see that energy came from here and went here. It's sort of hard to measure total energy because, you know, you would have to measure every last iota of energy, which means that maybe you'd have to take all of the energy out, and we've already talked about how silly that is with the absolute zero thing. So we have talked before about exothermic and endothermic as concepts, where exothermic means that you've got energy in the system and it flows out of the system into the surroundings. So if you have a log, for example, there's a lot of chemical potential energy contained in the bonds of the carbohydrate molecules in the log, and as it burns and forms more stable compounds like carbon dioxide, the net energy means that there's a lot of extra energy. And so that flows out of the system into the surroundings, and then your toesies get warm. And remember that exothermic reactions are represented with a negative sign, and stop doing that. Represented with a negative sign, so a negative delta H. And you'll need to remember that delta means change in, and that H stands for enthalpy, which is the total heat of the system. So, and you have to remember that your perspective when you're trying to make sense of these positives and negatives is that you are the system. So if you are the system and its exothermic energy is going out, you are losing it, it's going away, so it's negative. Whereas for endothermic, if you are the system and energy is coming from the surroundings into the system, then that's a positive, a gain in energy, so that's a positive delta H, a positive change in enthalpy. And one thing that you need to be certain on is breaking bonds versus forming bonds. When you form a bond, what you're doing is you're taking two atoms that are sort of far apart, and they are, because of their attractions, coming close and sharing their electrons, which is a more stable state. So when you form a bond, you go from an unstable state to a stabler state, and that means that there is energy that gets released from the system so that it's a more stable system. So forming a bond is exothermic. Breaking a bond, you have a stable system with a connection. You've got to break that and separate these two atoms that were attracted to each other. So you've got to break that bond and pull them apart, and that's endothermic. It requires energy to do that. The way that I remember it is I think of breaking bonds like you have to chop, and that's an input of energy. So there you are. Remember that. All right, so that's our first box, box number 2. We've talked about the first law of thermodynamics, which is that energy is never created or destroyed. And then the second law of thermodynamics is that the entropy of the universe increases. Again, you have to think of the universe and not just your system that you're considering. But in general, everything that we've ever observed shows that entropy increases in the universe. You can, within a particular system, if you add energy to that system, you can decrease the entropy within that system, but not within the universe, not within all things. And so, on a side note, I've heard people argue that certainly you can't have organisms become more complex over time, because that would be a decrease in entropy, and we know that the entropy of the universe increases. It's not a good argument, because you're just considering a system, and there is energy input to this system from the sun, so be aware of that. Doesn't work. All right. Entropy. The definition of entropy is basically disorganizedness or randomness in the system. So over time, things get more random, things get more disorganized. And the little example that people always use is, things get messy unless you put energy in to clean them up. So a typical teenager's room over time will go downhill and things will get messier and messier. And then you have to put input in to put stuff back where it's supposed to be into an organized state. On the molecular level, entropy as a disorganizedness is things flying all over the place and being crazy. And another way of looking at it is, if it would take longer to perfectly describe exactly what is going on with every single particle, then it's got more entropy. So if you have, there's a diagram in your book of two globes that are connected by a little tube, and in part A they have all of the molecules on one side and none of the molecules on the other side, and that is low entropy. Whereas in part B they have half the molecules on one side and half the molecules on the other side, and that's more entropy, because you'd have to because things are more disorganized and things are more randomly located instead of being in a nice neat pile on one side. That's entropy. One of the things to take note of is that heat in general is the most disorganized form of energy. So that's why when you have some process, you typically always lose at least a small amount of energy as heat. And once energy becomes heat, it's really hard to recover as a useful form that you can do work with. And so examples of this are heat in your engine, and the engine gets hot, and that's not particularly useful. What you want to be happening is the pistons going up and down, but all of the friction from the process going on of the combustion, you lose some of the energy from the gasoline as heat in the engine. If you want to increase the efficiency of your engine, you want to have less energy lost as heat, because it gets lost in the sense that you can't use it to do the work that you were trying to do. So since you always lose some energy as heat, no matter what you do, there's this concept of the heat death of the universe, which is, well, if things keep on going like they do and energy keeps from its useful work-able forms keeps turning into heat, then eventually we're going to get to a point where everything is totally spread out in the universe, and there's just kind of a vague low-level amount of hotness going around, but we can't really organize that energy into anything that we can use anymore. And that's bajillions of years from now. But since entropy always increases, eventually at the end, if the universe keeps going the way that it is, that's what would be observed. So a system, when it has less energy, like I was talking about over here, a system when it has less energy is more stable, and when it has higher entropy, it's more stable. If it's disorganized, it's hard to get it back organized. So it's pretty stable in a disorganized state, because what is it going to do? Probably stay disorganized. Is it going to organize itself? No, probably not. So systems are observed to either stay what they're doing or go to a lower energy, a higher entropy state. It's easy to lose energy. It's easy to get disorganized, but it's hard, and you have to input energy to get that stuff back. So because of that lower energy state being more stable, that's why we observe that exothermic reactions are more commonly spontaneous. Burning is something that's spontaneous. It will go. If you have, you have that little reaction written out of the log burning. Does the log burn? Yeah, it does. Do you have to constantly put in energy in order to make it go? If you flip that reaction around, you're talking about photosynthesis. Photosynthesis does not happen spontaneously. You have to kind of constantly kick it and go, here's some energy, here's some energy, here's some energy, here's some energy. So exothermic reactions are much more commonly spontaneous. They are typically thermodynamically favored. It's not always the case, and we're going to talk about why some endothermic reactions also can succeed and be spontaneous, and it has to do with the fact that it's endothermic, and so it requires energy, but it increases entropy so much that that kind of overcomes that problem. So we'll get to that on the next lecture. All right, so if you have your system changing energy, it's important to know that you are either putting you are either withdrawing or depositing some form of energy, and the forms of energy are either going to be as some kind of heat or as some kind of work, and that's this formula here, which is actually kind of the mathematical representation of the first law of thermodynamics, which is the change in internal energy of a system, and that's E, by the way. The change in internal energy of the system is either from heat or work done on the system or by the system. Q being heat, if you remember back to Q equals mc delta T, which we did last year. If you lose heat, heat goes out, then you're going to have a Q that's negative. If you have heat coming into the system, an endothermic process going on, then you've got a positive Q. And in your problems, you are going to need to notice whether it's positive or negative sometimes, so that you can assign the sign of the amount of heat or work. And then if you've got work that the system is doing, which the particular type of work that they are most frequently talking about when you're in chemistry. When you're in physics, you can do all sorts of different kinds of work, but the kind that you only really care about in chemistry is work that is done on the pressure and volume of a system that has a gas in it. So a reaction that makes a gas and then it expands against atmospheric pressure, for example, would be a type of work, or if atmospheric pressure squishes down on your system. So if your products, for example, expand against the atmosphere, it's doing work on the atmosphere. That would be work done, work going from the system into the surroundings. That's going to be a negative amount of work. Whereas if the atmosphere is compressing, it's called PV work. If the atmosphere is compressing and doing PV work on your system with some kind of gas in it, then work is being put into your system, and you're squishing this guy down, which gives him sort of a springiness, and so he's gaining energy in that sense, and so he's being worked upon, and that would be a positive work. So point is, the only way that your energy changes is if you put in energy or take out energy. That's what this formula says. Ooh. And the two forms of energy that you can kind of do that with is either as heat or work. But those are both forms of energy, which you can tell because the units that you have for E and Q and W are joules. And joules is the unit that you get out of the 1/2 mv squared formula that we were talking about before. And a joule is equal to the units off of this formula. So M, which is kilograms, and V, which is meters per second, but then it's squared, so it's kilograms, meters squared, seconds squared. So this complicated unit, kilogram, meters squared, seconds squared, they're like, that's not very pretty. How about we just call that a joule? Okay. Stop that. So 1 joule, if you've got an amount of energy which is equal to 1 joule, that's the same as the energy that you need to take a 2 kilogram object and in a span of 1 second accelerate it to 1 meter per second. So it's kind of taking a heavy thing and going, let's see, 2 kilograms, like 4 pounds. So kind of a wussy girl like barbell, and going, that's a joule of energy. Ooh. So it's actually a really small amount of energy. So There you go. All right. So we talked about internal energy up here. And one of the things that really confounds me is that there is internal energy and there's enthalpy. And they're very similar. They're nearly almost the same thing. Don't let it worry you that they are slightly different. What ends up being the case is that you can't really take the number that you get out of this equation and stick it into an equation with H, because they are slightly different, like 1% different, because internal energy is the energy that's contained in the heat of a system and contained in the potential energy of the chemical bonds of your system. That's internal energy. Enthalpy is the combination of that internal energy that we just mentioned, and there's a small amount of energy involved in the status of its pressure and volume right now. And so there's a little bit of extra energy involved in enthalpy than compared to internal energy, but you don't care. It's fine. The symbol for enthalpy is H. They're basically the same idea. It's the energy of the system, the heat content of the system. You just can't interchange them. Sorry. All right, enthalpy change. You've got your delta H. This is the energy that is released if it's exothermic, or absorbed if it's endothermic by that system when your bonds are broken. Now think to yourself, breaking a bond, chop, is endothermic, whereas forming a bond is exothermic because they're becoming more stable, so energy goes out. In order for you to actually measure an enthalpy change in the lab, because of this fiddly stuff about the energy of its pressure and volume, you have to make sure when you are measuring an enthalpy change that it's at constant pressure. That's sort of easy. That means you just do it in a room. You can't do it in a bomb calorimeter, which is an enclosed calorimeter, because then the pressure would change. Okay, woo. Here's a formula that's, I think, sort of an obvious concept, which is your change in enthalpy is going to be, well, how much enthalpy did I end up with, and how much enthalpy did I start with? Okay, subtract them. This is one of those end minus start formulas, like delta T, that you do the end temperature minus the start temperature when you've got these delta H, and we're going to have delta S, and we're going to have delta G later. It's always end minus start, so products minus reactants. So this isn't really a formula that you use so much as it's conceptual, like, hey, end minus start, okay? And again, the exothermic, you've got, with an exothermic reaction, your products are more stable than the reactants are. And that means that the bonds that are in the molecules of those products are very strong bonds, whereas the reactants of an exothermic reaction had pretty unstable bonds, and they were going, ah, and then they went, plah, boom. And now they have strong bonds, they're more stable, and the energy difference between these bonds and these bonds has gone into the surroundings. Whereas with an endothermic reaction, you have stable compounds with strong bonds, and you're going to have to break those strong bonds and make compounds with kind of unstable bonds. This is sort of a difficult situation to manage, so you have to put energy in order to break those bonds, because the net difference means that that's what you have to do. All right, calorimetry. We burned a Cheeto last year with a calorimeter, and our percent error was not great, but burning Cheetos is fun. Calorimetry is finding out how much heat is released when you do a thing, basically by heating up some water and seeing how hot the water got with that process. So we took a Cheeto and set it on fire and used that fire to heat up some water. We measured how hot the water got, and we went, ooh, that was this much energy. That's how much energy was in our Cheeto. That's the idea behind using a calorimeter. We used a coffee cup calorimeter, which is made of a coffee cup. No, wait. We used a Coke can because styrofoam burns. Yeah, you can't use a coffee cup calorimeter if it's actually on fire. Yay. We used a Coke can, and the problem that we had is that Coke cans are really poor insulators. So the energy escaped from our calorimeter, and so we didn't get to measure it. All right, so this is that formula that we've seen before, Q equals mc delta T. Q is your heat. We saw this formula. We saw that variable up here. Hey Q, hey Q. It's in joules. If the heat was gained by the system, it's endothermic, it's positive. If it was lost, it went out, it's negative. M is mass, so that's the grams of the sample. C is the specific heat capacity, which is how much energy is required to heat a gram of that substance by 1 degree. The value for water's specific heat is really important, and you have to have it memorized, and it's 4.184 joules per gram degree Celsius. And then delta T is change in temperature, and again it's the end minus the start temperature. If you have them flipped, you'll get it negative when it's not supposed to be. I'm sleepy. So that's Q equals mc delta T. If you're using this for calorimetry, which this is one of the funky WebAssign questions that I found. If you're doing this for calorimetry, what you have to be aware of is that the energy of your solution, dang it, stop that. The energy of your solution, the energy of the water and whatever reaction is going on in there, is equal in magnitude to the amount of energy that the water is absorbing, or and the calorimeter pieces are absorbing. It's equal in magnitude, so the number is the same size, but the signs are opposite, because for the solution, which is your system, the energy is going out, and for the calorimeter, the energy is coming in. So you can set the equations equal to each other, but with an opposite sign. So you could have you can solve for the Q of the first part, and then give it a negative sign and set it equal to what's happening to the water. That's a hint. All right. Oh, and also be aware that C is per gram of substance. That's your specific heat capacity. Sometimes they will give you molar heat capacity, which is how much energy is required to raise a mole of the substance by 1 degree instead of a gram of the substance. And if they give you that and you need C, you have to convert it and kind of divide by its molar mass. So be aware of that. Molar heat capacity will trick you. All right, next. Hess's law is something that's fun to do and comes up a lot, and if you know how to do it, you'll get a whole lot of points. There's a weird little idea that you need to understand before we can get to Hess's law, which is the concept of a state function. And not like the United States, but like, what state are you in? Not like Georgia, but like, are you in a state of fear? Are you in a state of calmness? So what is your current status? A state function is describes variables that it doesn't matter how you got there. You could take any path and the value that you get would be the same. And I know that doesn't make any sense yet, but the example that they use in the book that really helps me is if I'm going to travel from Atlanta to Chicago, I can travel from Atlanta to Chicago using a variety of paths. I could take a plane, I could drive my car on the highway, I could drive my car on the little small roads, I could maybe take a train. Is there a train? And the distance that I travel from Atlanta to Chicago, if I measured all of the distance, would be slightly different, because a plane uses a slightly different path as a highway car, as a train, as a byway car. So the path for distance matters. That means that distance is not a state function. However, the difference in altitude between Atlanta and Chicago, it doesn't matter how I get from Atlanta to Chicago, the amount of altitude change that I experience is going to be the same. I can go up and down the hills on the Appalachians and end up in Chicago, or I can go way up in a plane and then come back down to Chicago, but my altitude difference has been the same. That is an example of a state function. It didn't matter how I got there. I can take different paths and I'll get the same number. That's all you need to know. Hess's law depends upon this concept. So let's get to Hess's law. Sometimes it's hard to actually measure in a calorimeter the delta H of every single stinking reaction that you're interested in. For example, I was talking earlier about burning Cheetos. It's hard to measure in a calorimeter how to burn a Cheeto if your calorimeter is flammable. So just kind of due to practical considerations, you might have a reaction that you want to know the change in enthalpy for, but it's going to be sort of hard to do that in the lab. Hess's law says if you want to know the delta H for a particular reaction, instead of doing it in the lab, you can go look up a different path to get there. You can find several other reactions that if you add them up and cancel the pieces, you will get the reaction that you're interested in. And you can add up their delta H's, and that will give you this delta H. And so this is the same idea as the altitude. You know, you can do several different paths to get there. And you can, but you end up with the same numerical answer. So let's see. For example, here you've got C2H2 reacting with water to make C2H5OH. And if you look down at these two reactions, you've got all of these compounds present. You've got C2H2, you've got H2O, you've got C2H5OH. You've also got carbon dioxide, but it cancels. So let me show you, let me get my pen. Let me show you how you do this problem. All right, so you cancel your products to reactants until you get your original reaction. So this is the reaction that we're hoping for right here. And we're going to add these two reactions together, and because I've kind of preloaded this, these are the two reactions that will work. You add these two reactions together. So you go, okay, so the reaction that I want has got C2H2 as a reactant. Here's C2H2 as a reactant. Here, look, I took care of that one. Whee! And the reaction that I want has got C2H5OH as a product. Here's C2H5OH. And here's C2H5OH, so I've taken care of that guy too. Well, that's exciting. And let's see. Oh, well, we've got some oxygen though on here, and we don't want oxygen. So oxygen is going to need to be canceled. So this oxygen, 3 O2s, if you look at this one, will cancel with this. So you have this as a reactant and as a product, so it will cancel out. Because if something is present before and after something happens, it didn't really do anything. And same thing goes for our carbon dioxides. We have 2 carbon dioxides as products, and we have 2 carbon dioxides as reactants, and they didn't do anything because they just sat there. And then we've also got, now this one is kind of fun, you've got 2 waters on the right as products and 3 waters on the left. That means I can cancel these 2 with these 2, hey, with these 2, hey, it's doing that thing. Leaving 1 water, and notice that it's liquid, that'll come up in a second, and this water. So that means I have accounted for both of my reactants, reactant, and my product, and I've canceled all of the other junk that I didn't need. So I have basically recreated the reaction that I am interested in. Now, the enthalpy changes for these 2 are known. When I run this reaction, that is exothermic to the tune of 1411 kilojoules. And when I run this reaction, that is endothermic to the tune of 1368. And what that means is I can figure out that this delta H is 1411 negative plus 1368, which means it will be slightly exothermic. Negative 1411 plus 1368. That's going to be negative 43 kilojoules. So that is how you do a Hess's law problem. You cancel your products to reactants until you get your original equation, and then you add up the delta H's that you did. You have to make sure that everything cancels properly, or you can't do the delta H part. And then there are two more rules that you're going to have to use in the problems in a second, which is if you have a reaction that you want to use for Hess's law, but it's backwards, that's okay. You can flip it. So, for example, if I needed to have C2H2 on the right-hand side, I could just take this whole reaction and switch the products to reactants and have it backwards. What that does is it switches the sign of the delta H. So if I flipped this reaction, this would become delta H equals positive 1411 kilojoules. So that's one rule. If you need to flip it, you may, but you have to flip the sign. And then the other one is if it's not big enough, you can multiply it. So for example, if I needed to have two C2H2s, I could multiply this reaction by 2. I could say, all right, well, fine, that's happening twice. So 2 C2H2s, 6 oxygens, 4 carbon dioxides, 4 waters. And then you have to multiply the delta H. So that would be negative 2822 kilojoules. So flip it, flip the sign, multiply it, multiply the delta H. You can do both. You can flip and multiply. It's amazing. All right, here we go. Here are your problems. And we should take a pause and go do them. And then I will come back and give you the answers. All right, question 1. 100 joules of work are used to compress a gas. At the same time, the gas gives off 23 joules of heat to the surroundings. What is the energy change to the system? All right, so what we have is, we have some work and we have some heat. We've got, is my pen working? Hang on. There we go. We have work equal to 100 joules, and we need to think about which direction it's going. We have our system, which is the gas, and it's being compressed, it's being worked upon by the surroundings. So the energy from the work is coming into the system, so that's positive, endothermic. At the same time, the gas is giving off heat. So we've got some Q, which is equal to 23 joules, and we have to think about which way it's going. The gas, which is our system, is giving heat off to the surroundings, so that's a negative 23 joules for Q. So we've got some energy coming in the form of work and some energy going out in the form of heat. The energy change to the system is going to be delta E equals Q plus W, which is equal to negative 23 plus 100, which is equal to 77 joules. And remember that E is internal energy, which is nearly the same thing, but very slightly different from delta H. All right, question 2. The reaction 2NO plus O2 yields 2NO2, has a delta H, and then here's this little dot means in standard conditions, by the way, and we'll get to that on the next page, is equal to negative 114.1 kilojoules. This reaction contributes significantly to the formation of photochemical smog, NO2 being that brown hazy gas that you see in Atlanta. Calculate the quantity of heat released when 23.1 grams of NO is converted to NO2. All right, so you've got 23.1 grams of nitrogen monoxide. We need to know how many moles that is, because this amount of energy, the negative 114.1 kilojoules, happens every time you do 2 moles of NO. So we need to know how many moles we have. So grams of NO is 30.01. That's 1 mole of NO. And another equality that we know is that for every 2 moles of NO, you release negative 114.1 kilojoules. And that's going to give you, as your answer, negative 43.2 And how many sig figs did I give you? 1, 2, 3. Negative 43.9 kilojoules. All right, question 3. You have determined that it requires 5.0 joules of heat to raise the temperature of your coffee cup calorimeter by 1 degree Celsius. When you neutralize 50 milliliters of 1 molar sodium hydroxide with 50 mils of 1 molar hydrochloric acid, the thermometer rises from 22 degrees Celsius to 35 degrees Celsius. How much heat has been released with this reaction? Note, you may presume for now that the density of both solutions is 1 gram per mil. The density is actually slightly bigger, but I'm not going to make you calculate what the density of a dilute solution is. We're just going to go with 1. So what we have is Q equals MC delta T. Our delta T is going to be the end temperature minus the start temperature, so 35 minus 22. That's going to be 13 degrees. Your excuse me. Your C is the amount of energy required to raise the temperature by 1 degree, which I gave that. It's 5. So our specific heat is 5 joules per gram degree Celsius. And our mass is an interesting question. How much mass are we talking about? I don't know. All I know is volume. Yeah, but I also gave you density of 1 gram per mil, which makes it real easy. Your mass is the combination of these two here. So 50 mils, which weighs 50 grams, 50 mils, which weighs 50 grams. We've got a mass of 100 grams that we're dealing with here. And so our Q is equal to 6,500. How many sig figs did I give you? 2. I'm so good. 6,500 joules of energy were released. So it went out, so it's negative. Bing. Because I had said that much heat was released, I've already implied that it is going out, and so you don't have to include this negative, but just be aware of the going outness of it. All right, 4. The combustion of carbon monoxide is represented as follows. Carbon dioxide plus half an oxygen gives you carbon monoxide plus half an oxygen gives you carbon dioxide. Determine the value of the standard enthalpy change for the combustion of carbon monoxide at 298 K, which at 298 K, that's your standard conditions. That's why you have that little dot. Hey, little dot. Using the following information. It's actually hard to combust carbon monoxide, and so that's why we're going to be using Hess's law here. So here's the reaction that we want to recreate. And I always draw a line under it so that I know that's the one I'm going for. And we don't know the delta H. And so these guys, we've got to make sure that they end up matching. So what we need, we have this formula. C, carbon plus oxygen yields carbon monoxide. Carbon monoxide is one of the things that we need to match the top. So we're going to need to switch this reaction backwards. So that's going to be carbon monoxide yields carbon plus 1/2 oxygen. Okay, so that means this and this have been accounted for. So we've got that reactant, and we switched this, so that's going to be times -1 for that number, because we flipped it around. All right, this one, we've got carbon dioxide on the right-hand side, which is good because here we have carbon dioxide on the right-hand side. So let's go ahead and write this down here. Carbon plus oxygen yields carbon dioxide. And here's the carbon dioxide that we need, and here's the carbon dioxide that we need. That's great. And now we can cancel some things. Here's a carbon that we can cancel because we don't need it in the reaction that we're looking for. And if you look at the oxygens, it's kind of interesting. We have half an oxygen that we need, and a whole oxygen, and half an oxygen that we don't need. So we cancel this half, and we cancel like half of this oxygen. So this one and this one. So that means we have accounted for all of the things in this reaction by flipping the first reaction and using the second reaction as it is. So that means that we're going to have our delta H equal to 110.5 plus negative 393.5, which equals negative 283 kilojoules per mole. That is our delta H for this reaction, and that was a Hess's law problem. All right, number 5. Silane is highly combustible and creates a fire hazard as follows, which is silane plus oxygen is burning. Woo! And we don't know the delta H for this one. This one's a little bit harder. There's more stuff going on, so here we go. We need to recreate this reaction. SiH4 and 2 oxygens yields silicon dioxide and water. Be aware that the water is in its gaseous state. That's something that you need to keep track of with water, because sometimes they give it to you as liquid and you have to account for the fact that it's changed to gas, and that as an energy change. Doesn't look like they're doing that to you here. Nope. Okay, so we need to find the reaction with SiH4 in it, and that is, there it is, there's the first one, this one. And SiH4 is on the wrong side of this first equation, so we're going to need to flip it. And that means that's multiplied by -1. So that's SiH4 yields Si plus 2H2. And that's going to mean that we've got this reactant accounted for. Anybody else? 2H2. Oh, that's not supposed to be an O. Okay. And let's see, what's next? Silicon dioxide. We've got some silicon dioxide, and that's the right amount. It's on the right side, so we just copy this straight down. So silicon plus oxygen yields silicon dioxide. That means we've accounted for this. Anybody we can cancel? All right, and then the third one, we've got some hydrogens and some gaseous waters. Gaseous waters we need, but we need 2 of them. And, oh, and we also need hydrogens to cancel twice. So we're going to multiply this one by 2. So that's going to be 2H2 plus O2 yields 2H2O. And that's going to make this and this accounted for. And the hydrogens cancel out, and our 2 oxygens matches our 2 oxygens, which is beautiful. So in terms of the numbers, we've got -34 plus -911 plus 2 times -242, and that equals, well, what does that equal? -34 plus -911 plus 2 times -242. -1429. I thought it was negative. -1429 kilojoules per mole. That is the delta H for this reaction here, which would probably be hard to find because of its explosive, exploding nature. So it's not going to be real easy to stick that in a calorimeter and observe it easily without hurting yourself. So that's why you would do it with Hess's law. Ding. Thanks, folks.